Okay, in chapter 3, we were working on, composition of substances and solutions. And I believe where we left off was working with the concept of moles. Just as a quick review, remember that moles are just a quantity of a substance, just like similar to a dozen. And mole of a substance is always the same number of items. Just like a dozen is always 12 of something, a mole is always Avogadro's number, or 6.022 times 10 to the 23rd items, whatever those items are. They don't have to be atoms or molecules. You could be talking about donuts or something like that. And you could count those as numbers of moles also. You treat basically a lot of times in working out the difference between, well, we've got so many of this, how many moles is that? A convenient way to approach it is to think about what you would do if you were talking about dozens instead. So and I showed some examples the other day about how you could actually do that. You know, like if you have 18 items and you want to know how many dozens you have, you would divide by the number of items in a dozen. You'd say 18 divided by 12, that's 1.5. So you have 1.5 dozens. Same idea with moles. If you had 18 donuts and you wanted to know how many moles of donuts you have, you would just take that number and divide by Avogadro's number instead. And it would end up being a really small number of moles of donuts. But a mole has to have a lot of things in it in order to be an appreciable quantity that we can actually work with, because moles is usually, or the mole unit is usually used as a quantity of things like atoms or molecules that are really, really small. So you have to have a large number of them in order for it to be convenient to deal with. The reason this number was chosen instead of something more obvious or more easier to remember is simply that 6.022 times 10 to the 23rd power is the conversion factor between atomic mass units and grams. And so 6.022 times 10 to the 23rd atomic mass units would be equivalent to 1 gram. That's why they chose that number. This makes things very convenient because now the masses in the periodic table, which we have been thinking of until now as atomic mass units per atom. So like carbon, when we see the atomic mass of carbon is 12, we think of that as 12 atomic mass units per atom of carbon. That's nice to know, but there's not much you can do with it because atomic mass units are so small that you cannot measure them out reliably or accurately. On the other hand, though, now that we have Avogadro's number, we know that these masses in the periodic table also mean grams per mole. So carbon has a mass of 12 atomic mass units per atom, but it also has a mass of 12 grams per mole of atoms. And grams are a unit of mass that we can easily measure out with pretty good accuracy, and they're easy to deal with because they're large enough for us to see and feel and appreciate. And also using that information, you could find out if you wanted to, what is the mass in grams of 1 carbon atom. It would just be 12 grams divided by the number of items in a mole, 6.022 times 10 to the 23rd, and it would end up being a really, really, really small number, which just goes to show how small atoms and molecules really are. So that's a quick bit of the mole. And that led us up to the second section of chapter 3, which we were just about to start last time, and we will start now. This is about empirical and molecular formulas of compounds and how to determine them from experimental data. We went over a little bit of this in, what was it, the first chapter, I think, where we talked about finding molecular formulas from empirical formulas or vice versa. And we're going to go into it in a little bit more detail now. So first of all, for some reason, they've decided to lead off this section with percent composition. And percent composition is something that can be used in finding empirical and molecular formulas. So I guess this was probably as good a place to introduce it as any. So if you're wondering about, what percentage of a compound is made up of a certain element, what percentage of water is made up of oxygen, for example. Generally, a percentage is thought of as the part you're interested in over the whole thing times 100. So the portion part over the whole times 100 means the part that you're thinking about or interested in divided by the whole thing, whether you're dealing in units of mass or volume, and then you multiply that by 100. So essentially what you're getting is how much of the substance is made up of the part you're interested in per 100 parts. So you can also think of percentage as being sort of parts per 100. That literally is what percent means, actually. Percent in Latin means for every, and among other things. And cent comes from the word centum, which means 100 in Latin. So literally percent means per 100. So you can think of percent as being parts per 100. This is a very general way. Part of the whole times 100 is a very general way of looking at percentage. There are many specific ways of looking at percentage, depending on what type of percent you're interested in and what kind of samples you're dealing with and that kind of thing. But it always really boils down to this. So it's probably good to remember this because even if you forget the specific way to calculate a percentage in a given situation, by referring back to this, you can often figure it out. What is the part I'm interested in? What kind of units am I using? Am I talking about units of mass, or am I talking about units of volume? Those are probably the two most common ways to do it. Or am I talking about number of atoms or molecules? That's another way you can do it. As it turns out, each compound is made up of a constant percentage of each element. And that's always going to be true, whether you're talking about a single molecule of the compound or whether you're talking about a huge sample of the compound, billions and billions of molecules. The percentages will still be the same because each molecule is made up of the same proportions of the same elements. And we could actually measure these proportions in units of, say, mass or number of atoms. Mass is the more common and more important way to do it. So I'll just give a quick example of doing it by number of atoms first and get that out of the way so we can move on to the more important stuff. Water would be a good simple example. Looking at the number of examples, you could think of the percentage of hydrogen in water according to the number of atoms as being 2 hydrogen atoms over a total of 3 atoms in the entire molecule, 2 hydrogen plus 1 oxygen, which is 2 atoms over 3 atoms, the part you're interested in, which would be the hydrogen atoms, that's 2 atoms, and the whole thing, which is 3 atoms, which includes those 2 hydrogen atoms plus anything else that might be present, like the oxygen in this case. So that would be 3 atoms for the whole thing times 100. So it turns out 2/3 or 66.7% of water is made up of hydrogen atoms. And then for oxygen, actually a convenient shortcut when dealing with percentages is if you just remember the fact that when you add up everything in a sample or a compound, in this case, the total has to be 100%. So if you're on your last component and you've accounted for the percentages of everything else, the percentage of the final component is going to have to be 100 minus the percentages that you've already found. So in this case, percent oxygen should be 100 minus 66.7 because everything that's left is oxygen, and that would be 33.3%. Or you could do it the way we did with hydrogen, and if you look at an H2O molecule, you have 1 oxygen atom. That's the part we're interested in if we want percentage oxygen, and there are 3 atoms total. The 1 oxygen atom and the 2 hydrogen atoms for 3 atoms total, and that gives 1/3 times 100, which is 33.3%. And this will be true of water no matter how many molecules you have. If it's water, the formula of each molecule is H2O, and you will have twice as many hydrogen atoms as you have oxygen atoms, which means 2/3 of all the atoms present will be hydrogen, and 1/3 of all the atoms present will be oxygen. And that'll always be true, again, of water, no matter how much or how little you might have. Okay? So to move on to mass next, we can also use water as an example. And when you're dealing with percentage by mass for the elements in a compound, you can use either the empirical formula or the molecular formula, because either way, the percentages come out the same. It's just that the molecular formula is some whole number multiple of the empirical formula. And when you multiply the empirical formula by some whole number to get the molecular formula, you're essentially multiplying the numbers of atoms you're interested in by that number, but you're also multiplying the total number of atoms by that same number. And so the percentage will still come out the same. So using water just as a simple example, if you're looking about, say, per atom, you could say, okay, in hydrogen, there are 2 atoms of hydrogen, and each of those atoms has a mass of 1 atomic mass unit. So that would be 2 times 1 AMU. And the entire molecule of H2O, if you look that up in the periodic table, there's 1 atomic mass unit for each of the hydrogens and 16 atomic mass units for the oxygen. All of that together is 18 atomic mass units for the whole thing. So that would be 2 times 1 over 18 times 100, and that gives 2 over 18 times 100. That's 11.1% hydrogen. You can also now that we know about the mole, it's actually even more convenient to think of those masses from the periodic table as being grams per mole. So if you take water, actually for that matter, if you're looking at the percent by mass of hydrogen and oxygen in water, or the elements in any compound, you could take any quantity of the compound that you want to. You could look at 1 atom, or you could look at a mole. Those would be the 2 easiest ways to do it. But you could use any quantity of the compound, and it should come out the same. So looking at it in terms of, say, 1 mole of H2O, well, 1 mole of H2O contains 2 moles of hydrogen, because however many H2Os you've got twice as many hydrogens, because there are 2 hydrogens per molecule. You know, it's like saying, if you've got 10 cars, how many tires do you have, not counting the spare tire? Well, that would be 40 tires, right? Because there are 4 tires per car. So we've got 2 hydrogens per molecule. So if we have a mole of molecules, that would mean that we have 2 moles of hydrogen. So 2 moles of hydrogen, and hydrogen has a mass of 1 gram per mole. And the entire molecule, if you've got a mole of it, that would come to a total of 18 grams per mole. So again, that's 2 over 18 times 100, or 11.1% hydrogen. For oxygen, the percent by mass would be the fact that you've got 1 oxygen per molecule of H2O, and therefore you've got 1 mole of oxygen for every mole of H2O. However many H2Os you've got the same number of oxygens, because there's 1 oxygen per molecule. So for 1 mole of H2O, there's 1 mole of oxygen, and oxygen has a mass, according to the periodic table, of 16 grams per mole. The entire molecule still has the same mass. It's still H2O, so it's still 18 grams per mole for the whole thing. So again, you've got the part you're interested in, which would be the oxygen part of H2O, over the whole thing times 100. In this case, that comes to 16 over 18 times 100. That's 88.9%. The other way you can handle this is just by taking, since oxygen is the only other element there besides hydrogen, you can just take 100 minus the percentage of hydrogen, and that gives you the percentage of what's left. These percentages by mass should turn out the same way, no matter how much or how little oxygen you use. Again, as little as 1 molecule or a mole or as much as you want. The only thing is if you're not using like either 1 molecule or 1 mole, the math gets a little bit harder, but it should still come out the same percentages. Notice though that the percent by number of atoms is different than the percent by mass. And that's because different elements have different masses. There are twice as many hydrogens in each molecule of oxygen, but or of water, I mean, but oxygen weighs a lot more than hydrogen does. So in percent by number of atoms, hydrogen is the vast majority of water, but in percent by mass, turns out oxygen is the vast majority of the mass of of water. It's kind of like in a car. If you look at, say, each car has 4 tires, but only 1 engine. So in terms of percentage by numbers, tires are way ahead of engines. But on the other hand, the engine is a lot heavier than the tires. So if you go by percent by mass, the engine makes up a lot more of the car than the tires do. Okay. So as another example of percent by, say, experimental data, percent by mass from experimental data, we could say we had a 150-gram sample of water, and our data from our analysis shows that 150 grams contains 16.67 grams of hydrogen and 133.33 grams of oxygen. So what would the percent by mass of hydrogen and oxygen be based on the experimental data? Well, the percent hydrogen would be just the mass of the hydrogen over the mass of the entire sample. So again, it's the part we're interested in over the whole thing. So 16.67 over 150 times 100, and look what it comes out to be, 11.1% again. For the oxygen, again, since that is the last element present and there's nothing else besides hydrogen and oxygen, you could just say 100 minus 11.1. But if you want to use the numbers from the experiment, you could do it that way too. And that'll be 133.33 grams of the part we're interested in, the oxygen, over the 150-gram sample for the whole thing. And that's 88.9% by mass oxygen, which is what we got before, just looking at 1 molecule. So again, should come out the same as long as it's the same compound. We talked before, now we can finally get into empirical formulas. We talked in the previous chapter about empirical formulas and what they are. So remember, it's just the empirical formula is the lowest whole number ratio of the elements in a compound relative to each other. And in some compounds, the empirical formula is the same as the molecular formula. In some compounds, they are different. Empirical formula is called that because, well, the word empirical refers to experiment. And so empirical formula is called empirical formula because it's often the formula that you get from directly from experimental data. And if you want the actual molecular formula, then you need additional data beyond just the empirical formula. So for something like H2O, that's the molecular formula, but it's also the empirical formula because there's no ratio simpler than 2 to 1. Okay, so sometimes the empirical and molecular formulas are the same, sometimes they're different. For hydrogen peroxide, the molecular formula is H2O2, but the empirical formula is HO because a 2 to 2 ratio can be simplified by dividing the subscripts by 2, and you get 1 to 1, which is HO. So in this case of hydrogen peroxide, the molecular formula is the empirical formula times 2. Okay. So looking at an example of actually getting the empirical formula from experimental data. Sorry. We've got an example here. If a sample of a compound containing phosphorus and oxygen is found to contain 6.549 grams of phosphorus and 8.451 grams of oxygen. And its sorry, molar mass, that is the mass in units of grams per mole, is known to be 284 grams per mole. What are its empirical and molecular formulas? So first you would find the empirical formula, and you can do that by using the mass of each element that you found from your sample. And so the first question you'd have to do is find out how many moles of each element you've got in that sample. Because in order to find the empirical formula, you need the relative ratio of number of moles of one atom to another. So for phosphorus, it would be the 6.549 grams of phosphorus divided by the atomic mass from the periodic table, which is 30.97, which I'm just going to round off to 31. Okay, where are we? 31. And you can take the 6.549 grams and just divide by 31 grams per mole, or you can multiply by the reciprocal of the atomic mass, which would be the fact that there's 1 mole for every 31 grams of phosphorus. It accomplishes the same thing mathematically, but when you multiply by the reciprocal, in other words, you multiply by 1 over the atomic mass, it makes it much easier to track what's happening with the units, and that makes it easier to make sure that you're doing things the right way. So grams of phosphorus will cancel with grams of phosphorus because this grams of phosphorus is in the numerator and this is in the denominator. So the units cancel and you end up with 6.549 divided by 31, which is 0.2113, and the unit would be moles of phosphorus. Do a similar thing with oxygen, 8.541 grams of oxygen. The periodic table tells us that the atomic mass of oxygen is 16 grams per mole, or in other words, 1 mole for every 16 grams. Again, multiplying by the reciprocal of the atomic mass makes it easier to watch the units. Grams of oxygen will cancel, leaving you with moles of oxygen as the unit, which is what you wanted, so that's a good sign. And 8.541 divided by 16 is 0.5282. Okay. So now we found the moles of phosphorus and the moles of oxygen in that sample. And what we need to do now for the empirical formula is find the relative number of moles of one element versus the other. And to do that, what you do is you divide both numbers of moles by whichever one is smaller. And the result will be the subscript in the empirical formula. Okay, so for phosphorus, we take 0.2113 divided by itself. That's obviously 1. For oxygen, it's 0.5282 divided by 0.2113, which is 2.4976 something, something, something. And that you can round off to 2.5. Okay, generally when you get a number that's really close, now, I mean, normally you'd want to round off to the nearest whole number, but you can also end up rounding off to the nearest half number sometimes, because that's just sometimes the way the data work out. If you were using actual experimental data from an experiment we actually did, then sometimes it would be kind of iffy. You know, it would be hard to know whether you should round that off to the nearest whole number or whether you should round it off to 2.5. But if you're working with an example that I made up or that the book made up, you can be relatively sure that there's a small enough amount of experimental error involved that you can round it off to basically what it looks like. And this really looks like 2.5 here. That's really close to 2.5. So go ahead and round it off to 2.5. And if either of these numbers is not a whole number, that's a problem, because you can't have fractional numbers in the empirical formula. They have to be whole numbers. Well, there's a way that you can get both of these numbers to be whole numbers without changing the relative ratio of the two. just by basically multiplying them both by 2. If you multiply 2.5 by 2, you get 5. To keep the ratio the same, you also have to multiply the 1 by 2. And so the subscript for phosphorus becomes 2, and the subscript for oxygen becomes 5. So the empirical formula is P2O5. That's the empirical formula, though, because that's what we get directly from the experimental data. For the molecular formula, we have to compare the molecular mass of the empirical formula to the molecular mass, the mass of an entire molecule. So what you do is you take the molecular mass over the empirical formula mass, or in other words, the bigger one over the smaller one. And in this case, the molecular mass back in the problem was quoted as, where is it? 284 grams per mole. And you, when you go to the periodic table and add up the masses of 2 phosphorus and 5 oxygens, that's because that becomes 2 times 31 plus 5 times 16. That adds up to 142 grams per mole. So 284 divided by 142 is 2. That means that the actual molecule is twice the size of the empirical formula. So you multiply the subscripts in the empirical formula by 2, and that becomes P4O10. That's the molecular formula. And if there's any doubt, you can always check your answer by going to the periodic table and finding out the molecular mass of P4O10. Take 4 times 31 plus 10 times 16, add them together, and you'll find out that it is 284, just like it should be. And if it's not, then something went wrong. Now, what went wrong may be that maybe you just added up the masses from the periodic table wrong, but it would still, either way, it would mean that you definitely need to go back and check something, because there's a mistake somewhere if it doesn't work out. Okay, that I think takes us through part A of this little lecture. So I'll stop there and save the video, and I'll be right back.